In lecture 5, we're going to look at sampling and estimation. Sampling and estimation. So the basic core of this lecture is basically to understand the concepts of estimation and what statistical approaches you use for estimating certain parameters. We'll also consider what is called parametric interval estimation, where we will calculate the confidence interval based on predetermined confidence levels. We're also going to look at non-parametric interval estimation. So to start with, we have to understand the central dogma or the central key principle of statistics. So we have an entire population from which a small sample that may represent the entire population will be collected. So this is what we call a sample. This is what we call a sample. So a sample by definition is simply a subset of an entire population. An entire population is simply called a census. And so sampling is very important for a lot of reasons. There are two key reasons: financial and time. Because we do not have all the time, we cannot do a research on the entire population. And so we'd rather go for a sample. The second reason is that financial constraints. We may not have adequate funding because research is kind of very, very costly. So we may not have all the funding to do our research, and there's a time constraint. Also, a sample is sufficient for estimation. So we would rather go for a sample to represent the entire population. So a sample is already a representation of the entire population. So a sample is a subset of the entire population. This population is called a census, and a small proportion is called a sample. So under estimation, we're going to look at a few key variables. But before we go there, you may probably want to know, why do we conduct sampling? So sampling is important, like I said: time constraints, financial constraints, representation of the sample. A sample may be enough to represent the entire population. So it's sufficient to approximate this entire. So for somebody to know your blood group, they don't need to drain the whole blood. They will do what? Just get a sample. And also the destructive nature of sampling relative to the confidence level. You may need to just spray a few plants to know whether this is effective, not the whole portion. And finally, the universe size. No matter how much time and money you have, it may be almost impossible to do what? Conduct an exact sampling for the entire population. For instance, knowing how many babies are born, it's just an approximation that we have. Also, the accuracy level sometimes will be higher for a small sample. So smaller the sample, the higher the accuracy level. And so we're going to look at two key formulas in this. Whenever you're being asked to find the sample size, they're asking you to find n. N is given by z times the variance over the margin of error squared. The other formula that we're going to use when calculating the sample is z, the p times the q, divided by the level of precision, which is the error squared. So these are the two formulas that we're going to look at under sampling. These are the two formulas that we're going to use under sampling. Now, sampling has a number of types that you need to know. There are about two key categories of sampling. There's what we call probability sampling and non-probability sampling. Probability sampling is mainly about numbers. When dealing with probability sampling, we're actually giving every member an equal chance of being what? Of being sampled. And non-probability not every member has an equal chance of being selected because there are other factors that the researcher or the sampler will consider. For instance, convenience or judgment. So if we're going to subdivide sampling procedures, there is what we call simple random sampling under the probability methods, number one. There's what we call systematic sampling under probabilities about numbers. Systematic, like the way we type, every 10th, if you're going to look at people or customers who are with Zanak. So on the road, every 10th person you find, that's systematic. You're using a particular number. But if you're randomly selecting them after shuffling them, that is simple random. We also have under probability sampling, what we call cluster sampling. Cluster sampling, where you're going to subdivide a population into small groupings, which are called clusters. They may have a mini representation of the entire population. For instance, among the Tongas, you go in southern province, you pick 10. Among the Bembas in northern province, you pick 10. Rundas, from each province, pick 10, 10, 10, 10. Then from there, you pick a sample. That is called cluster sampling. Then we also have stratified sampling, where you're going to subdivide the population into subgroups based on one or more distinguished characteristics. For instance, the middle management, top management, and lower management. These are called strata. These subgroups are called what? Strata. So this is very important on a theoretical basis because the questions will ask you sometimes to define the two types of sampling. And under non-probability sampling, we also have two major types, which is convenience sampling, where you're going to pick a sample based on the researcher's easy access, because you stay in the same locality with the respondent, so you'd rather pick a certain sample. Then we also have what is called judgment sampling, where you're going to pick based on your professional knowledge. Not everyone who's brilliant is able to talk in public or represent a school. So as a researcher, you decide to choose a vocal person in class to represent you. So that is what we call judgment or purposive sampling method. So that is about the theoretical part. Now, these formulas here we're going to look at under sampling. There are only 4 formulas. Before we go any further, we also need to understand what is an estimator. An estimator is simply a statistic whose value is used to estimate the entire population parameter. And an estimate is simply a particular realization of an estimator. So we have different types of estimators. We have a point estimate, we have an interval estimate. A point estimate is simply a single number that can be regarded as a most representative or pausable value of the value of theta or the population. Then the interval estimate is simply a range of numbers, which we call confidence interval. So estimators have their own characteristics. Now, we've come up with another new term, which is called the confidence interval. The confidence interval is a range of values that we need to consider. So there's a table of a song that we studied yesterday, where we're going to have 4 columns. We have CL, which is called the confidence level. We have the SL, which is called the significance level. We have the alpha, and we have the Z. Okay, can somebody help us fill in? We have 4 common confidence levels. Number 1, we have what? 99, then?
98,
Then?
95,
Then?
90.
90, correct. So the difference from 100 is called our significance level. Who can help us with the significance level? 1%, then?
2%,
Then?
5%,
Then?
10%.
10%. So the relationship that the confidence level has and the significance level is that they should add up to 100. It's like P and Q. If this is P, the remainder is a Q. So this is how the relationship is. And when you divide the significance level by 100, you get the decimal, which is called the alpha value. So our alpha here is 0. What? 0.01. Followed by what? 0.02. Then followed by what? 0. What? 0.05. We're just dividing these figures by 100. Then finally 0.1. 0.10. Now at this stage here, since we're using a two-tailed test, we now need to find the values of what? Of Z. How do we find the values of Z? We use a table. Okay, so now we have what we call the statistical table here. Now, the statistical table has its own way of being read. We can read from Z to P and from P to Z. So I'm going to be as basic as possible. For those who missed just 4 minutes, you'll learn how to read this special X-ray report for a statistician. So the probabilities here total up to 1. So the reading for the Z value is as follows. If you're reading 1.23, you go under 1.2, the first two values, then the last value 0.03 is the one that you're going to check into the table. So we're using the Z value only here. We're not considering any T values. I'll teach those ones later on. So for now, it is just a Z table that we're looking at. So 1.23, you go under 1.2 and 0.03, where they meet at 0.8907. So the Z of 1.23 will give us a probability of what? 0.8907. Can you help me? Who can help us find the probability of 1.96? Who can help us find the probability of 1.96? What do we do? Probability of 1.96, what do we do? So we go to our Z table. 1.96, how do we get it? We go under 1.9. So 1.96, how do we read this? We go under 1.9. Then which other part do we look for? 0.06. Okay, so where are they meeting? 1.9 and 0.06. So the reading here is what?
0.975.
975. So if I gave you the probability as 0.975, then he asks you to find the Z for this probability. So this will be 1.9 and 6 there. All right, if I asked you the reverse way, so here we found 0.9750.
75.
So suppose I asked you to find the value of the probability, which is 0.9800, 0.9803. Help me find the Z for this one, 0.9803. Let us locate this. What is the Z for this one? 0.9803. Can somebody quickly locate that?
0.9.
It is here, right? So what is the reading?
Oh, we're working in reverse now. Okay, that's 2.06.
2.06, correct. We're working in reverse. So this is 2.06, correct. Now, sometimes you may not have the exact figure, but something close. Suppose you're being asked to find our Z figure of 0. Of the probability 0.9 0.9130. Can you help me find the Z for 0.9130? So let's go to the table. Help me identify 0.9130. Which one is closest, or is it exactly?
1.36.
1.36.
36. Mhm.
Are we agreeing? So this is 1.36. We're agreeing with him. So this is 1.36. Okay. How about 0.9500? 0.9500.
1.605. 1.65.
1.65. How about if someone says 1.64? Would they be wrong? Which one is closer?
Actually, both there's an intersection there.
Yes, both equidistant. So what we do in that case, this one, so you go in between. So you start with the smallest one, 1.6, then add a 5 at the end. So it becomes 1.645. All right, 1.64, then you add a 5. The 5 is because you said they're in between. If it was between 7 and 8, it would be 1.675. If it was between 8 and 9, 1.695. So on the smallest figure, you just add a 5 at the end. So this gives us 1.645. Otherwise, you will not be penalized if you picked either of them. There are exceptions. Now, we go to this table here. How do we do it? So to start with, we use a two-tailed because we're dividing by 2. A two-tailed estimation and sampling are always under a two-tail. So these are the two tails there. I'll teach you later on how to do with the one tail. I can even teach you now since you guys are not bad at all. So I'm going to start with 95. The reading for this one is just to find the Z is simply 1 minus alpha over 2. For a two-tailed. If it's a one-tail, alpha over 1. So what is the alpha for 95? It is 0.05. So 0.05, we divide by 2. What we're going to get is 0.975. So when you check this one inside the table, 0.975, we've already learned how to read this from inside the table. We will find it here at 1.96. So meaning the Z at 95% would be what? 1.96. Let's try the Z at 90%. Who can help us in the procedure? What do we do? 1 minus what? Alpha.
1 minus alpha over.
And our alpha is what?
0.1
Divided by 2.
divided by 2, yeah.
Final answer we get is 0.975. 9500. So when you check this inside the table, we already found it. It gave us 1.645. So I want you to try find at 98% on your own quickly. 98%. Can somebody take us through the procedure? Number one, what do you do?
It's the same procedure.
Mm-hmm.
1 alpha over 2.
Okay, so the same procedure. So the first step, we're going to do what? 1 minus what?
Alpha over 2.
Okay. We're going to have 1 minus alpha over 2. And at 98%, what is our alpha?
0.02.
0.02. What we do, we divide by what? By 2.
Yeah, we divide by 2.
Then what do we get?
Choose 0.02. We get we are going to have 0.02 divided by 2.
We're going to find 0.99.
0.01, then 1 minus, it's giving us 0.99.
So what do we do with 0.99?
Then we go into in the table. We look at where we can see 0.99 inside the table. Yeah.
So check inside the table.
Somewhere at 2 point. Yeah, it's at 2.33.
Yes, 2.33. Here, this one here, right? 2.33.
Yeah.
So 2.33. So this is why this is about 2.33. And if you do the same procedure, this will give you 2.58. That's why these are the most common percentages that are given. No wonder instead of you going through the trouble, I summarize this table for you to memorize it. So we learned a song yesterday that the first two are twos. 99, 98, 258, 233, 95, 90, 196, 1645. These ones are easy to understand. All right. So let's go through the song again. Confidence level, we have what? 99, then 98.
98, 95,
Mhm.
90.
So this is a section where ladies do very well because they're good with memory. They're able to remember what you did when you wore what and what you said the exact way. Now let's channel that energy, memorizing these ones here. So our confidence level, we know the order. I'm really interested in the Z. Everything points to the Z. So here, what is our first Z?
2.58.
Then
2.3.
then 1 point.
96.
Then 1 point.
645.
Excellent. All right. So this confidence level in terms of significance level, same as what? In terms of alpha, it's the same as what? 1, 2, 5, and what? 10. 0.01, 0.02, 0.05, and what? 0.10. This we're okay with this, right? All right. So sample size is given by two formulas: Z squared variance over the margin of error. Z squared PQ and the margin of what? Error. This is with the sample size. With the confidence interval, we have two formulas as well. Mean, here we have Z over square root of N. Then here we have confidence interval is equal to proportion plus minus Z. Then here we have PQ over N. We know that when P is 10%, the remainder is Q. So this formula is being given. We are now going to use our small examples. So we find the missing. Find N if our alpha is 0.10, our standard deviation is 6, and our error is 4. But B, find the sample size if our confidence level is 95% and our variance is 16 and our error is within plus minus what? 2. So here we're going to use the formula. Remember the formula? Z squared variance over the error. So let's substitute. Where the Z, what are we going to put? From where the Z, what are we putting? 1.645. You need to master the song. This is same as 90%. And what is our standard deviation? 6. And what is our error? 4. So 1.645 times 6 divided by 4. We're going to get 6.088. Okay, 6.088. So that's a sample size. In the next instance, we're also looking for our N. The formula for N is what? Z over the variance divided by the error squared. At 95%, our Z is what? 1.96. And our variance is 16. We're not going to square it because it's already in variance form. Or if you want, you can put 4 squared, it will get back to the answer. We're not squaring it because we're given as what? Variance. So when you calculate that, you're going to find your sample size as 15.3664. Sometimes we'll be given, find the sample size when your proportion is 30% and your error is within plus minus what? 5%. Here, the formula that we use. So the formula that you use is determined by what? The variables that you're given. So if you're given PQ, we know that when P is 30, meaning the Q should be 70%, the two must add up to what? 100. So our Z here will be what? If you're not given Z, the standard is 95%. So here is 0.01. 0.01 we are given. What is our Z? Who remembers? Our song needs to be a part of you. 2.5.
1.7.
So people usually confuse the 1% and the 10%. So you need to be careful with the decimals. All right. So here we're going to find what? 70%. These ones don't square them. And the percentage is what? As follows. So when you compute that, you're going to get your sample size, which is 559.14. All right. Let's try another one. Suppose you're being asked to find the sample size, and you're given your confidence level at 98%, and your proportion is 0.4. Who wants to try? How do we find our sample size? What formula do we use? N is equal to Z squared PQ over what? E squared. What is our Z?
2.33.
2.33, correct. And what is our P? 0.4, meaning what is our Q?
0.6.
The 2 must add up to 1. And our error? Okay. So when we calculate that, we're going to find our sample size. Our sample size will be calculated from that. So we get 3,200 and what? 57.34. So it's just an issue of understanding your formula. Now, there's what we call confidence interval. If I were to ask you how long does it take for you to drive from home to school, you will just give an approximation. There are people who are bad at approximation, it is villagers. Ask them how far it is to the clinic. They'll say, Apple, when you need to walk miles and miles. So you need to be very good with estimations. And this is one part where doctors really need to be a participant of certain estimations they give within which a patient must tolerate their resistance should be within their knowledge. So if you are bad at estimating, you may lose a life. So you're told that if you say it takes you 50 minutes to walk from your work, from your home to your school, then if you're going to give a margin of error, maybe you say 10 minutes plus minus. So what does this mean? If you're early, you're going to be there in 40 minutes. If you're late, you're going to be there in what? 60 minutes. So this is what is called your confidence interval. It's a range of two values. These two values have a lower boundary, which is a lower limit, and the upper limit. So this will help us go backwards. It helps us find our mean. Our mean is simply the lower boundary plus the upper boundary divided by what? By 2. And our error is simply equal to our lower boundary minus the upper boundary divided by what? 2. So with this being the case, we're now going to do what? We're now going to evaluate. Let's see whether if we're going to add these two, we're going to get this mean. So 40 plus 60 divided by 2 will give us 100 over 2. Are we getting 50? Yes, we have found the mean as 50. Then we go to 40 minus 60 divided by 2. We're going to get negative 20, or you can put the 60 there. It doesn't matter because the error is a range. Divided by 2, we're going to get plus or minus 10. So we found our error term here. So I'm using basic knowledge. So now to combine what we're just from learning, suppose we're told that what name can I choose? Helena. The confidence interval for Helena's walk from home to school is between 40 and what? And 60. She makes 100 trips in a week to go home and school. At a confidence level of 2%, find Helena's standard deviation. So we're going to use, this is a 10-mark question. We know that our n is equal to z s over what? E. So we've been asked to find the standard deviation and the mean. So to start with, we have our sample size, which is 100. Our z here, can somebody tell us what is the z at 2%?
0.33.
2.33, correct. We can find our mean by averaging these two. What is the mean? 40 plus what?
Add
60.
the lower bound. Okay.
It will give us a 50, correct. We can also find this error here since that has not been given by the difference of the two, 60. So you can put the absolute figures there so that you get a plus minus there. So it means 40 minus what? 60 divided by 2. So what we get? Plus or minus what? This is 20 divided by 2, which is 10. So the error is 10. So we now substitute here where there's n, put 100. Where there's z, 2.33. But in the formula, it's supposed to be square. Then the s squared over the error squared. Our error has been calculated as what? 10. So cross multiply. So this one, we are going to have 2.33 squared times s squared is equal to 100 times what? Times 10 squared. So we divide both sides by 2.33 squared, even here 2.33 squared. So this cancels. So we're going to have s squared is equal to what? 100 times 10 squared divided by 2.33 squared. So it will give you 1841.99. This is not the standard deviation, but the variance. So to get a standard deviation, we know that it is the square root of the variance. So when you square root that, our final answer will be 42.92. This is how it is supposed to be done. All right, 42.92. Now, confidence interval also has its own formula. The formula for confidence interval is simply the mean plus or minus the z, the standard deviation over the square root of n, if we're using a sample. And Z is only used for samples more than what? 30. Less than 30, we use our T table. Well, that is a lesson for another day. You will notice that the sample sizes that I'll be concentrating on for now will be more than 30. So we'll be asked at A, find the confidence interval if we're given our mean of 100, our mean is 10, then we are also told our alpha is 0.05 and our n is 64. All right, and our standard deviation is 16. So we know the confidence interval. This is the formula. So we'll start where there's mean, we put 10 plus minus. So sometimes the formula will give you this ugly thing here. Don't mind it. I've already told you that estimation and confidence level is always a two-tailed test. So our sum is already fulfilled here. So what is our Z here? From our sum, what is our Z? 1.96. And our standard deviation is 16. And our N is 64. So
How do you find the Z?
we already have a sum, we're past that. I'm sure I've already explained how this is done. There are 4 confidence levels. The Z is supposed to be calculated from the table. So I've asked you to memorize this. All right. Those of you who were in my class, help me or help him remember. Just give me the Z figures. 0.05, 2%, 95%, 0.10, 90,
8%.
and put 90%,
Or 9.
just randomly putting them. 10%, 0.02, 99%, 0.01. So what is the Z for this one here? For 0.05, what is our Z here? 1.96.
96.
What is our Z here?
That's 2.33.
0.33. What is our Z here?
1.96.
1.96. What is our Z here?
That's 1.645.
Yes. Or we can even use 1.65. It's okay. Or we can use 1.64. It's okay. They're all acceptable. Here,
One 1.65.
here,
1.65.
here, so this is a song that you need to have. It will guide you. If you didn't get the procedure of how to get this, please get through the video. Are we moving together? Am I losing anyone? This is one of the toughest, but I've been very careful to take you step by step. So, calculating, we're using Z because our sample size is more than 30. If it was less than 30, we would have used the T. And the T has its own procedure of reading. So, the square root of 64 is 8. 8 into 16 is 2. So we're going to calculate that. We'll multiply 2 times 1.96. So what we get? 3.92. 3.92, when you subtract from 10, we get 6.08. And when we add, we get 13.92. So this is how we do the confidence interval. Part B, sometimes we have to find the confidence interval. Again, we're given our mean is 20. Our sample size is 36. And our variance is 144. We're also given that our alpha is 0.02. So we use the same formula. What's the formula? Confidence interval is equal to what? Who can remind us? Mean plus or minus z, standard deviation over square root of what? N. So our mean is what? 10, is 20. We already have this. And our z, what is our z here? 2.33. And what is our standard deviation? The square root of the variance. So this will be our 12. And our sample size is what? 36. Sometimes the standard error will be as follows. If you're given the variance, you can put it all of it in the square root to still give you the same figure, because you're going to square root it either way if you want to put it together, because people have a problem here. You don't understand that this is a variance. A variance is a square of the standard deviation. So here we're going to have 20 plus minus 2.33. Then here we're going to have 12 over the square root of what? 36. So when you compute that, you're going to get a 2 in there. 6 into 12 is 2. 2 times that one would be 4.66. So 4.66, you start with firstly the lower boundary. So 20 minus 4.66 would be 15.34. Then when you add that, you're going to get 24.66. So this is the upper bound and the lower bound. And your comment would be in terms of the confidence level to say we are what? We are 98% confident that the true mean will lie between 15.34 and 24.66. If you don't know how to comment, just leave it as it is. This is called our confidence interval. Finally, we'll be asked to find the confidence interval, but what will be given are proportions. They're given a proportion of what? 20%. And your sample size is 50. And you're being asked to find what? A 99% confidence interval. Find the 99% confidence interval. So to find 99% confidence interval, we're going to use what? Formula number 2, which is the proportion, which is P plus minus Z PQ over square root of everything here. So our P is 20%. So we'll put 0.2. What is our Z? From the 99, 2.58. And if P is 20%, what is our Q? Q is 1 minus P. So if P is 20%, Q should be 80% or 0.8. So these things speak to each other throughout. They're consistent. These speak to each other. They're consistent. The sample size is 50, not 50%. We wrote this here. So this is what? 50. All right. So when you calculate we're going to have 0.2 here, plus minus 0.2 times 0.8 divided by 50, then you square root the answer, then times 2.58, you can just do it together, which is 0.41459. So you can put them in percentage if you want. 20% plus minus what? 14.59%. And you subtract. Here we're going to get 5.41%. And here we're going to have 34.59%. So the comment is in terms of the confidence level, we are 99% confident that the true proportion will lie between 5.41 and 4.59%. So this is how confidence for proportions goes. This is how the proportion goes. So you now go to your assignment questions that you'll be asked. So I will look at some of the questions that you are most likely to cover today. So suppose a customer has an average what? 78.25 and the population standard deviation, which is 22.5. We're being asked to find a 90% confidence interval and a 90% for a different sample orders. So let's try this and see quickly within 3 minutes. I know people are supposed to go back. Given a question as follows. Suppose a random sample has an average. So let's identify what has been given. What we have? Number one, our mean. Our mean has been given as what? X bar will be what? 78.25. The standard deviation has been given as what? 22.50. In part A, we're asked to find the what? 90% confidence interval with a sample size of what? 40. So how do we find this? Mean plus minus z standard deviation over square root of n. So here we're going to have what? 78.25 at 90. What is our z? 1.65 or 645. Same. Then here we're going to get 22.50, and our sample size in this case will be what? Our sample size in this case will be 40. The same will be done for the second one, except that here the sample size will change to be what? To be 75. So what the examiner wants now to test you on is to understanding what's the difference between the two. The confidence interval that has a bigger margin in terms of accuracy, and the confidence that has a smaller margin. So you need to comment in terms of that. So you need to understand that if we have a bigger margin, what does it mean? Does it mean that there's a higher accuracy level or there's a lower accuracy level? So this is the solution. So the formula is as follows. A 90%, you can calculate the standard error separately if you want. Okay, so Z 1.64, I said 65, 64, 645 same. Then the standard error is the same as this. This is a standard deviation over root of n. it will give you the standard error. I can separately do it if you want, which is 3.55. So when you compute them there for a sample size of 40. So since here we're using a sample size of 40 here, you see how the confidence level we're getting, the confidence interval that we're getting at 40, we're going to have the following. At 40, our confidence interval will be between 72.41 and 84.09. So based on the sample, we are 90% confident that the true proportion will lie between 72.41 and 84. So this is the confidence interval. So at the sample size of 40, it's between 72.41, 84.09. That is where the sample size is. I want you to look this critically. And if you use a sample size of 75, when you compute all this, it's a standard error. You just put it here, standard error changes, and you're going to have 78 and what? 78.99 and 82.51. So which one has a larger margin? So the comment is, although both are 90% from the same proportion, the size of the intervals differed due to the difference in the sample sizes. So you notice that the larger the sample size, in the problem resulted in part 2, the confidence interval was smaller. Then where we had the other thing, the smaller sample size, where the confidence interval which was higher. So this is precisely where we're going to conclude that if intervals of the same confidence interval have different sizes, then we need to know that a smaller confidence interval is more precise. It's a more precise estimate of a population. So if you're giving an inference about which one has a more precise, we have 10, 13, this is your range, and we have 9, 20. So which one of the two has a more precise confidence interval? A or B? So A is more precise because the margin of difference is smaller. You're more confident. You're asking how much do they get as accountants or as civil servants? You're going to say between 6,000 and 7,000. And somebody will tell you how much they get in government as civil servants. You get between 2,000 and maybe 7,000. The one who's more precise, the one with a smaller margin. So this is what we're trying to talk about here. So with that being said, I'll give you homework based on the class that has been done.